Hello, and welcome to Linear Algebra. This is lecture 25 on orthonormal bases. Okay, so last time we talked about the Cauchy-Schwarz inequality. So this takes place in any inner product space. So recall that we're now assuming that our underlying field is either the real numbers or the complex numbers, and that our vector space is endowed with an inner product. Right, so this time we want to talk about another concept that makes sense on inner product spaces, and that is a basis of orthonormal lists. Okay, so let's start straight off with the definition. A set of vectors, right, column v sub I, could be infinite. Is orthonormal if the inner product between any two of them is either 0 when j is different from k, or it's equal to 1 if j is equal to k. Right, so i.e. it is a list, it is an orthogonal list. It is an orthogonal set of unit vectors. Okay, if B is a list, if V1 through Vn, and it's orthonormal, and it is a basis of V, we call it an orthonormal basis. Okay, so we have our usual example, the standard basis. Is orthonormal with respect to the standard inner product. Another example, consider the list 1 over square root of 2 times the vector 1, 1, and then 1 over square root of 2 times the vector 1 minus 1. This is an orthonormal basis of R2 or of C2, right? With either standard inner product. This is an orthonormal basis. Okay, orthonormal bases are very convenient to use. For example, it is easy to find the coordinate representation of a vector with respect to an orthonormal basis. So if B, consisting of V1 through Vn, is an orthonormal basis of V, and then you pick any vector in V, right? So we want to find its coordinates. Remember, the coordinates of a vector with respect to a basis are the coefficients when you write that vector as a linear combination of the basis vectors, right? So let's say that this vector satisfies W is equal to A1 V1 plus dot 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 AN Vn, right? So then A1 through AN are the coordinates of this vector with respect to this basis. So I want to find the coefficients. Well, the thing to notice is that if now I take the inner product of W with any one of the basis vectors, let's say Vj, then let's see what we get. So for W, we can substitute A1 V1 plus dot 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 AN Vn, and then we're taking the inner product of Vj, right? And because the inner product is linear in its first entry, I can write this as A1 times the inner product of V1 with Vj plus dot 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 plus AN, the inner product of Vn with Vj, right? But because we're working with an orthonormal basis, I know that each of these inner products is either 0 or 1. And all of them are 0 except for the inner product of Vj with Vj, which is equal to 1. So here in this sum, the only term that survives is the one where I'm taking the inner product of Vj with Vj, and I end up getting just Aj. Right? So wonderful. We wanted to find the coefficients of this linear combination, and by taking this inner product, we have found the jth one, right? So we can conclude that the basis representation, the coordinate representation of W with respect to the basis B is inner product of W with V1, then the inner product of W with V2, and so on until the inner product of W with Vn. So much simpler than if you had an arbitrary basis with no orthogonality condition. You don't have to solve any system of equations or anything. You just take these inner products and you find the coordinates one at a time, but straight away. Okay, similarly, if you want to find a matrix representing a linear map, it's much easier if you can work with orthonormal bases. So it is also easy to find the matrix representing a linear map if the basis of the codomain is orthonormal, right? So I only really need one of the bases to be orthonormal, the basis of the codomain. So say T is a map from V to W, linear map. And recall that for any basis VV with vectors V1 through Vn of V and VW of W, the matrix associated to T with respect to these bases, well, you can find this matrix one column at a time, as we usually do. And the way you do that is for the first column, you would take the first basis vector of V, and then you would express the image under T using the basis of W, right? So this column would be take T of V1 and express it using the basis W, right? And so on, and until the last column would be T of Vn, expressed in the basis of W. And that's the matrix, right? So we find the matrix one column at a time. And since all you need is the coordinates of this vector with respect to this basis, if this basis is orthonormal, then we just saw that you can do this very quickly, right? So let's write it down. If BW is an orthonormal basis, then the vector T of Vj represented with respect to the basis BW would have entries, coordinates T of Vj, inner product with W1, dot, 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 up to T of Vj, inner product with Wm. Right, where I'm representing B of W as W1 through Wn. Well, but now if we look back at the matrix, we can say that the ijth entry of the matrix representing T with respect to the bases B, V, and BW is the inner product of T of Vj with Wi. Okay, so now we can find the entries in this matrix one at a time, but straight away. We have a formula for the ijth entry. Right? Whereas before, this involved solving a system of linear equations. Or multiplying by change of basis matrices or something like that. Here we can just find each entry on its own straight away. Okay, another thing that becomes simpler with orthonormal bases is the inner product itself, right? So let's say that I have an orthonormal basis and then I have a couple of vectors inside the vector space. Let's see how we can express the inner product of U and W using this basis, right? So what we can do is we know how to write U using this basis, right? I can write U as the sum of some coefficients, but I know the coefficients, times Vj. And similarly, W, I can write as a linear combination of the Vj's, but I already know the coefficients. So let me use a separate letter just to avoid confusion. So here I'm summing using K, and over here I'm summing using J. Okay, so now this is an inner product, and so we know that it's linear in the first entry and conjugate linear in the second entry. So I can pull out these sums. And I'll have, well, let me do this in 2 steps. So I pull out the sums. And so here I'll have the inner product of U with Vj times Vj. And here I'll have the inner product of W with Vk times Vk. Okay, now this is a scalar and this is a scalar, right? So I can pull this out just by itself, and I can pull this out with a conjugate, right? So this becomes sum j goes from 1 to n, sum k goes from 1 to n of inner product of u with vj times the inner product of w with vk conjugate. And then what's left? Well, in the first entry, I'm left with the vj, and in the second entry, I'm left with the vk. Okay? Now I stare at this. Remember, this is an orthonormal basis. So the inner product of vj with vk is either 0 or 1. It's going to be 0 unless j is equal to k, in which case it's equal to 1. Right? So that means that in this double sum, really the only terms to survive is when j is equal to k. So I just have a single sum, right? So I have the sum, j goes from 1 to n. So here I can set, so that's j in here. Instead of k, I can put j. Right? And then it gets conjugated. And then this term I no longer have to write because it's just equal to 1 when it's not 0. Okay, so we found the inner product. Right? In fact, right. So the inner product of u and w, we have written using only the inner products of u and w with respect to the elements of the basis. And we can recognize this. This is the standard inner product of the coordinate representation of u with respect to b and the coordinate representation of w with respect to b. Right? So this is really cool. So we know that if I have a finite dimensional vector space, say if of dimension n, right, over a field f, then every time I choose a basis, I get an identification of that vector space with f to the n. Now suppose you have an inner product on your vector space. So if you pick a basis, you've identified it with f to the n, but the inner product is still just some inner product, right? It's not necessarily related to the standard inner product on f to the n. However, what we've just seen is that if the basis you picked is orthonormal, then not only are you identifying the space with f to the n, you're also identifying its inner product with the standard inner product of f to the n. Right, remember here, f is either the real numbers or the complex numbers, so we have a standard inner product. Okay, in particular, let's see what this says about the norm. The norm of a vector u squared, right? Remember, the norm by definition is just the inner product of a vector with itself, right? But the inner product vector with itself, well, we have a formula for that using the basis. The sum j goes from 1 to n of the inner product of u with vj times the inner product of u with vj conjugate, right? Okay, but now I have a complex number times its conjugate. That's equal to the modulus squared of the complex number. Okay, so this is the usual norm of a vector in Fn, right? So we're just getting you start with your vector u, you represent it with respect to an orthonormal basis, and then its length is just the same as the length of that vector with respect to the standard inner product. Okay. So those are some of the reasons why it's really useful to have an orthonormal basis. So then a natural question is, well, when do we have an orthonormal basis? And we're in luck. Always. Every finite dimensional vector space with an inner product has an orthonormal basis. Okay, how do we know? Well, here's how to find one. Okay, so this is known as the Graham-Schmidt process. Okay, so we can think of this as a theorem. I'm going to describe an algorithm, and then the claim is that this will produce an orthonormal basis, and then we'll prove that that claim is true. Okay, so first let's describe the algorithm. So first, start with any basis, let's say U1 through UN of V. Okay. Define V1 to be U1 divided by the norm of U1. Okay. Then, for any j between 1 and n, we're going to define the vector Vj in 2 steps. Okay, so what we want to do is we want a vector Vj that is very close to Uj, but we want it to be orthogonal to all the vectors we end up with. Right? Well, since we're constructing this one vector at a time, it's enough to guarantee that this is orthogonal to everybody who we've already constructed. So how are we going to guarantee that? Well, what you're going to do is subtract as much of the previous vectors as you can find inside Uj, right? So you can think of this as subtracting off the projection of the other vectors onto Uj, right? And when we started talking about inner product spaces, we talked about the projection of one vector onto the span of another one, right? So that's what we want to do. We want to start with Uj and subtract off from all of the previous vectors we've constructed their projection onto Vj. So the Vj will be as independent of the previous vectors as possible. So the way we'll do that is we'll define a Vj tilde to be, we'll take Uj and then subtract as much of Vj as you can find in the previous ones. So what we're going to do is Uj V1 times V1, and then Uj V2 times V2, until Uj against Vj minus 1, and then space, times Vj minus 1. Okay, so we start with the vector Uj, and then we're going to subtract off as much as we can from the V1 through Vj minus 1, right? So if the vector Uj were in the span of V1 through Vj minus 1, this would be the coefficients from what we've seen before, right? Of course, it's not in the span of these guys, so this is not going to give a 0, but that subtracts off enough to make this orthogonal. Okay, and then second, okay, so we'll have something that's orthogonal, but it might not be a unit vector, so now we force it to be a unit vector. So we'll define Vj to be Vj tilde divided by the norm of Vj tilde. Okay, so then V1 through Vn is an orthonormal basis of V, and moreover, for each k between 1 and n, the span of V1 through Vk is the same as the span of U1 through UK. Okay. So that's the claim. And now we will prove it. Okay. The proof will be by induction. So we will prove by induction that V1 through Vk is orthonormal, and that the span of V1 through Vk is equal to the span of U1 through UK. Okay. In particular, once you get to k equal to n, then you're done. It's being an orthonormal list, it's automatically linearly independent. And then if it spans the same as U1 through UN, then it spans all of V. And so we have an orthonormal basis. Okay. For k equal to 1, remember for k equal to 1, all you do is you say V1 is equal to U1 divided by the norm of U1. So this is true. Right? So it is an orthonormal list because it's just a unit vector. And the span of V1 is the same as the span of U1 because it's just a non-zero multiple of U1. So assume this is true for V1 through Vk minus 1. Right, so and by this, of course, I mean these statements. So assume that this is an orthonormal list and that it spans the same as U1 through UK minus 1. Okay, so now notice that since UK is not in the span of U1 through UK minus 1, right, which by inductive hypothesis is the same as the span of V1 through Vk minus 1, Vk tilde is not the zero vector. Okay, so let me scroll back up. Vj tilde is equal to Uj tilde minus this, and this is a linear combination involving V1 through Vj minus 1. So it is in the span of V1 through Vj minus 1, which by inductive hypothesis is the same as the span of U1 through Uj minus 1, and so is not equal to Uj. Right? So we're guaranteed that this is not the zero vector, and so this definition makes sense. We're not dividing by 0. So Vk is a unit vector. Okay, so to check that the list V1 through Vk is orthonormal, we just need to check that the inner product of, say, Vj with Vk is equal to 0 for every j less than k. Right? So in principle, we would have to check the inner product of any two vectors in this list. But because of our inductive hypothesis, we know that this list is orthonormal. So the only inner products that are left to check are the ones that involve Vk. And we have, okay, so the inner product of Vj with Vk is equal to the, okay. What is Vj? Well, Vj is equal to 1 over, no, let me not worry about Vj. Let's do Vk. So this is Vj, and then I have the sum, let's say L goes from 1 to, sorry, let me start. Okay, Vk is, by definition, 1 over the norm of Vk tilde times, in fact, let me just do that, Vk tilde. Okay, right. On the other hand, I can write Vk tilde as Uk minus the sum when L goes from 1 to k minus 1 of the inner product of Uk against Vl times Vl. Okay, this is what Vk tilde is. Okay, so now there's this constant, so I will go ahead and pull that out. It comes out as a conjugate, but actually that's a real number, so I don't need to worry about that. So I can just pull it out here, 1 over Vk tilde. Okay, and so I end up with the inner product of Vj with Uk minus the sum L goes from 1 to k minus 1 of the inner product of Uk against Vl times Vl. Okay, and now we'll use that this is additive in the second entry to write this as norm of Vk tilde times, so we have first the inner product of Vj against Uk, and then minus the sum L goes from 1 to k minus 1 of the inner product of Vj against inner product of Uk Vl times Vl. Okay, so all I've done is separated out this term and the sum, and then pulled out the sum. Okay, now this is a scalar, so I can pull it out. Oh, sorry, not there. It can be pulled out here. It's in the second entry, so I should pull it out with a complex conjugate. Okay, so I can write this as 1 over the norm of Vk tilde. And then I have inner product of Vj against Uk. And minus the sum L goes from 1 to k minus 1 of this inner product. Just get to pull that with a complex conjugate, and then this inner product Vj with Vl. Okay, now because the V's, here I'm only working with indices that are less than or equal to k minus 1. So by inductive hypothesis, they are from an orthonormal list. So this inner product is either 0 or 1, and it's 1 exactly when j is equal to L. So I can get rid of this sum because only the term when L is equal to J survives. So I can write this as 1 over the norm of VK tilde. And then I just have Vj inner product with UK minus, and only a term called J is equal to L survives, and this is a 1, so I don't need it, so I just keep its coefficient. So I have the inner product of UK with Vj complex conjugate. Now remember, in the inner product, if I switch the order of the vectors, I pay with the complex conjugate. So this guy is the same as this guy. And since I'm subtracting them, this whole thing is equal to 0. Okay, and of course that's where we wanted. That's what we wanted to show. Right? We wanted to show that this inner product was equal to 0, and by writing out everything in gory detail, we ended up getting 0. Right? So, okay, so this shows that V1 through Vk is orthonormal. Right, so that leaves us one more thing. We need to show that the span of V1 through Vk is equal to the span of U1 through UK. Okay, wonderful. So Vk itself is certainly in the span of U1. Well, actually, here, let's do it in 2 steps. So V1 through Vk minus 1 and UK, right? How do we know that? Well, here is Vk is equal to this, right? So I have some scalars, and then the vectors that show up are UK and V from L goes from 1 to K minus 1. So the vectors I need are UK and V 1 through Vk minus 1. Now, by inductive hypothesis, the span of the first few is equal to the span of corresponding U's. So this is equal to the span of U1 through UK minus 1, and I add UK. So the span of V1 through Vk is contained in the span of U1 through UK. Okay, wonderful. So I have a vector space and then another vector space, and this one is a subspace of this one, right? Now, since the dimension of the span of V1 through Vk is equal to K, and that's equal to the dimension of the span of U1 through UK, these spaces, these vector spaces, are equal. So are the same vector space. These are the same vector space. Right, because I have a subspace of the same dimension as the total space. So as we've seen before, that means it has to be equal to the total space. Okay, so we're done with the proof. What we've shown is that this algorithm, the Gram-Schmidt algorithm or process, starts with any basis you like and then produces an orthonormal basis of the vector space. Okay, let's see an example. So consider the standard basis for polynomials. let's stick with degree 2, and let's say real coefficients. So remember this space, we have many possible inner products. Let's use the inner product where you integrate between 0 and 1, f of x times g of x. If I were working with complex coefficients, I would put a conjugate over g of x. But since we're working with real coefficients, I don't need it. Okay, with this inner product, the basis, right, the standard basis for polynomials, so 1x x squared, is not orthonormal. Right? So why not? Well, for example, the inner product of 1 against x, right, would be, by definition, integrate from 0 to 1, the function 1 times the function x dx, and that's equal to 1/2, which is not equal to 0, which is what we would get if we had an orthonormal basis. Okay. However, fortunately, we have an algorithm now that starts with any basis you like and produces an orthonormal basis. We can use Schmidt to obtain an orthonormal basis, right, which would be V1, V2, V3. Okay, so, right, this is an orthonormal basis of this vector space. So each of these is going to be a polynomial. V1, right, is just going to be U1. So I'm going to, these would be U1, U2, U3. Right? So U1 divided by the norm of U1. So here that's going to be 1 divided by the norm of 1. Now the norm of 1 squared would be the integral between 0 and 1 of 1 times 1, so 1 squared dx, and that's equal to 1. So we already had a unit vector. When I divide by 1, nothing happens. So V1 is just the polynomial 1. Okay. Now, V2. So to find V2, we proceed in 2 steps. V2 tilde is going to be U2 minus the inner product of U2 with V1 times V1. Right? So what's that in this case? Well, U2 is the polynomial x, and then the inner product, so this would be x minus the inner product of x against 1 times 1, right? But we've already computed the inner product of 1 against x. That's the same as the inner product of x against 1 because I'm working with real numbers. Otherwise, I would put a complex conjugate. So we end up with x minus 1/2. Okay, that gives us V2 tilde. Let's compute its norm. The norm of V2 tilde. Well, the square of the norm would be the integral from 0 to 1 of x minus 1/2 times x minus 1/2 dx, right? And that is equal to 1 over 12. So that means that the norm of V2 tilde is equal to the square root of this, so 1 over the square root of 12. And so V2, which is V2 tilde divided by the norm of V2 tilde, is equal to, okay, well, it's the square root of 12. Let's simplify that. That 12 is 4 times 3, so square root is equal to 2 times the square root of 3. So I can write this as x minus 1/2 divided by 1 over 2 times the square root of 3, right? Or same as square root of 3 times 2x minus 1. Okay, and that's our second basis vector. So now V3, again, we'll find in 2 steps. V3 tilde would be U3 minus U3 inner product with V1 times V1 plus U3 inner product with V2 times V2. So in this case, U3 is x squared, and then I'm going to subtract the inner product of x squared against v1, that's just function 1 times 1. And then I'm also going, and then plus x squared inner product with v2. V2 is square root of 3 times 2x minus 1 times v2 square root of 3 times 2x minus 1. Okay, so that expression is going to give us V3 tilde. So I will jump ahead and tell you the answer. If you compute that, you get x squared minus x plus 1/6. Okay, so then we want to know the norm of V3 tilde. Right, well, the norm of V3 tilde squared would be equal to the integral from 0 to 1 of x squared minus x plus 1/6 times x squared minus x plus 1/6. And if you work that out, you get 1 over 180. So V3 is going to be x squared minus x plus 1/6 divided by 1 over 180. And so that's, square root of this. And so that's square root of 180 times x squared minus x plus 1/6. And hence, one orthonormal basis of the polynomials 3, 2 with real coefficients with this inner product is 1, and then square root of square root of 3 times 2x minus 1, and then square root of 180 times x squared minus x plus 1/6. Okay, so that's the end of the lecture. Next, I'll talk about some historical context, but feel free to stop listening now. Okay, so for the historical context, I thought I would tell you about one of the mathematicians. We've been dropping a lot of names in the last few lectures once we started inner products, but one of those names was Cauchy. And so I thought I would tell you a little about that mathematician, Augustin Louis Cauchy, who lived from 1789 to 1857. He is certainly the most important, most famous of the names we've been dropping recently. He is one of the most prolific mathematicians ever. He wrote 789 articles, which is incredible. It's amazing. He was one of the first to state and prove rigorously the theorems of calculus. Before that, there was a lot of hand-waving. He didn't do it all on his own. Weierstrass played a huge part as well, for example, but he was one of the first. You may have heard Cauchy sequences. You should have heard about Cauchy sequences. It's the same Cauchy. So his life was very interesting. He, as you can see, he was born in 1789. He was born 1 month after the revolution started, the French Revolution. His father worked in the police in the Ancien Regime, and so the revolution was not good for him. So they fled Paris right away and stayed away throughout the terror. They had a terrible time when they were gone. Cauchy would later talk about remembering not having enough to eat, having to scrounge for bread or only eating rice for days at a time. But they did all right. They survived. After the terror ended with the death of Robespierre, they went back to Paris. And then once Napoleon took power a little bit later, after the fall of the Directory, Cauchy's father did very well under Napoleon. He became Secretary General of the Senate. And so he worked for Laplace, who is another famous mathematician, and was good friends with Lagrange, who was also involved with the Senate. So these two great mathematicians, Laplace and Lagrange, were close friends of the family. And Cauchy grew up knowing them. Lagrange in particular seems to have taken an interest in Cauchy's education and really encouraged him to focus on languages, actually, because this would be really useful when he started his university education. Cauchy started out as an engineer, and he went to work. Napoleon was in charge, and Napoleon wanted to invade England. So Cauchy was sent to work in Normandy on the coast facing England, trying to set up the port to be ready to launch an invasion of England. But after a few years, he realized that really what he enjoyed was the mathematical aspects of his work, and he really wanted to devote himself to math. So he went back to Paris and started his mathematical career, but things were not going well for him at first until Napoleon fell and the Bourbons returned to power, and then Cauchy, who was a pious Catholic and a reactionary in his politics, was a huge supporter of the monarchy, and he was promoted and thrived as when the Bourbons were in power. So there were positions, academic positions, that he hadn't been able to get, that he was able to get once he had political connections that could help. So this was good for him. So then when this stopped with the revolution of 1830, it was not good for him. He was really shaken up when the Bourbons fell from power. And he ended up leaving Paris, right? So in 1830, as you know, the Bourbons fell. The monarchy did not fall, it was just replaced. The House of Bourbon was replaced by the House of Orleans, with Louis Philippe I, replacing Charles X. The new regime required all government employees, which included professors, to swear an oath of loyalty. And Cauchy really refused. He thought it went against his Catholic faith. He thought it went against his politics to swear an oath to a liberal regime. And in particular, he did not want the regime to succeed. He wanted the Bourbon to come back. He wanted Charles X to come back. And so he refused. And this meant that he lost all of his positions. So he wasn't going to be able to make a living as a mathematician, as a professor, without swearing this oath of loyalty, so he left Paris. And so he goes and he works in Switzerland and Sardinia and in Prague. He went to Prague because that's where Charles X and his heir had ended up. He was hired, Cauchy was hired, to be the tutor to the heir of Charles X, a guy called Henri d'Artois. But he's more famous under his nickname, the Miracle Baby. So that's a fun story. So when Henri was born, it looked like the Bourbons were going to die out. There were just not enough males in the Bourbon line for the monarchy to continue. It looked like the last three kings of France were going to be Louis XVI, who had the revolution happen to him, and then Louis XVIII, right? Louis XVII was the title given to Louis XVI's son, but he never reigned. Louis XVIII, who was the one who took the throne when Napoleon was defeated, and then his brother Charles X. So you were going to end in these three brothers. And the thing is that Charles X, although he did have sons, they did not seem to have any heirs. And one of them, the Duc de Berry, had lots of sons born outside of his marriage, but no legitimate children. And it looked like the monarchy was doomed, or at least the House of Bourbon was doomed, when in 1820, he was assassinated at the opera. It was used a lot as a morality play because he was assassinated after the opera was over, he went to he walked out his wife, got her into a carriage. She was going home, but he stayed behind because he had a mistress in the opera, and so he was going to see her. And as he was walking back to the opera, he was assassinated by a Bonapartist who wanted the family of Napoleon to be back in charge. So, but in a dramatic twist, it turned out that the Duc de Berry's wife was pregnant when he died. She was 2 months pregnant, so nobody knew at the time. 7 months later, she gives birth to a son, Henri. And so he's known as the miracle baby. One of his middle names was Dieudonné, given by God, a gift of God. But in any case, it didn't help the Bourbon in 1830. They were still kicked out of France and ended up in Prague. And then Cauchy goes to tutor this boy. And it was a terrible match because Cauchy was a terrible teacher. Throughout his life, he was a terrible teacher. There are lots of stories about his lectures and nobody understanding, or he starts a class and he ends the class at the end of the semester with only one student left. So it was 3 years during which Cauchy didn't produce any new math, and Henri d'Artois did not learn any math. He ended up with a lifelong hatred of mathematics thanks to this experience. But Cauchy was given the title of Baron by the exiled Charles X, and Cauchy was very proud of this and used the title the rest of his life. He goes back to Paris after this ended. This ended because the Henri d'Artois got to 18 and refused to have a tutor anymore. So Cauchy goes back to Paris and he sort of makes do. He still can't get his professorships back until 1848, when there's another revolution and the House of Orléans falls and the Second Republic starts. And now there is no loyalty oath required, and so Cauchy gets back his position as professor of École Polytechnique. And he's happy there until the Second Republic falls, soon after, 3 years later. They had elected Napoleon's nephew, and he saw fit to hold a referendum and have the people of France declare him emperor. So he took the title of Napoleon III, and Napoleon II being the title given to the King of Rome, as he was known, Napoleon's son, who also never reigned. Fortunately for Cauchy, even though Napoleon III brought back the loyalty oath, he made an exception. One of only 2 exceptions was given to Cauchy to allow him to keep his positions without taking the oath. And Cauchy died during the reign of Napoleon III, so he didn't have to worry about what came next. Cauchy was an amazing mathematician. He made fundamental contributions to complex analysis, the theory of numbers, group theory, differential equations, optics, mechanics, elasticity, and the wave equation. For us, for linear algebra, he did 2 important things. He studied the determinant, which we will get to at the end of the semester. And also, he proved one of the most important theorems that we'll cover this semester. It's called the Spectral theorem for symmetric matrices. Cauchy proved this in 1829, which, incidentally, is before Cayley defined a matrix. That seems very unreasonable, but you can state the theorem as a theorem for something called quadratic forms, and that's the form in which Cauchy proved it. Also interesting, he was widely disliked as a person. He didn't get along with many people at all. Part of that was that he was very in your face about his Catholic faith. Like, he would bring this up when he was discussing Newton's theorems and things like that, where it didn't seem to have much of a place. And but also he was very acerbic. He didn't like giving people credit for things they had done. This didn't help him There were many positions, like being in the academy or some of the professorships that he wanted that were elective, and he would often do very badly in the elections. The electors were the other professors or the other members of the academy, including one time he went up for a position, he received 0 votes for it. But although he was disliked as a person, he was universally admired as a mathematician. And so often he would eventually get the position he wanted, even if it took years or decades for that to happen. Okay, in any case, that's Augustin Louis Cauchy. And we'll stop there and pick it up there next time.